We are going to review some function transformations. We've seen this material most recently in terms of trig functions, but they also apply in pretty much the same way to any kind of function at all. And as we kind of head towards wrapping up the year, I want to make sure that you guys can sort of see how all the pieces fit together that we've been learning about. So here I have the graph of a polynomial. It's x cubed minus x. If you wanted to, you could factor this, greatest common factor, then difference of squares, to find that the three zeros are at x equals -1, x equals 0, and x equals 1. That's what we see here on the graph. It's an odd function. We can notice some other things about it. But the reason that I picked this function is that it's not a super standard function that you're extremely used to seeing the graph of, but it has a shape that is easy to understand while not being so simple that you can't see what's happening to it. So we're going to kind of see what happens to the shape of this function as we do different transformations to it. So the first transformation that I want to look at is when we add a number to the end. So I'll go ahead and enable this graph. And now this blue graph is showing the same function, but with the number a added to the end. And I have a slider here that lets me choose what I want that number a to be. So for example, I can make a equal to 1, and then it takes the entire graph of the function and moves it up 1 unit. This graph is zoomed in pretty close, so this here is 1 unit from this point to this point. So each point on the original red graph got moved up by 1. We can also move it down by making a equal to -1, or we can move it further down, a equals -2. So to write the equation of this blue graph here, it's g of x plus a, but I have a set to equal -2, so it's g of x plus -2, which would be the same thing as -2. So really, I could write the same equation, or by saying something like y equals x cubed minus x minus 2. That's what this a equals -2 slider is doing. It's putting a -2 on the end of this graph. Okay, so hopefully that makes sense. Really, I'm kind of taking this original equation and modifying it in a certain way by doing this. Okay. This transformation is pretty easy to understand how it happens. This is our equation that gives us the y value, and then we're adding some positive or negative number to that, which means that each y coordinate is going to change by that amount. So if I add 3 to the end of the equation, then every output that I would normally get is going to be increased by 3, which means that I get the graph shifted upwards. This one's pretty easy to understand. Let's now take a look at this transformation, something like g of x plus b. So now I have something added or subtracted from x on the inside of the equation as opposed to on the outside. And you might remember that this causes the graph to, oops, wrong slider. This b causes the graph to move horizontally, but in kind of the opposite way from how you would expect. If I make b equal to +2, that actually takes each point and moves it left by 2 units. So for example, the 3 x-intercepts, the 3 zeros of this polynomial, have moved from -1, 0, and 1 to -3, -2, and -1 when I set b equal to 2. Let's take a look at what this would actually entail to write it in the equation. So if I was going to write a y equals equation equivalent to this g of x plus 2, I would need to take this original equation, y equals x cubed minus x, and I would need to take every x and replace it with x plus 2. So x plus 2. That's what this replacement is really doing. It's taking every x in the original equation and plugging in instead x plus b, and in this case b equals 2. So it's basically taking the equation and replacing it every x with x plus 2. Or if I make b equal to -3, for example, that would be like taking every x and replacing it with x plus -3. That gives me the same graph. So the green is, and the blue graphs are the same as each other, just written in a different way, with the green graph showing us kind of how we're changing the original equation, and with the blue graph just being the actual changed equation. Now, it's kind of weird to write this plus -3. Most of the time, we probably would just write that as -3. And we can see that that moves us to the right by 3. And because these x coordinates sometimes work in the opposite direction, a lot of times, instead of writing this equation as plus b, we might write it as minus b. Oops. Shoot. And then the slider kind of works again in the way that we would expect. Get from -5 to 5. So if we do this, looking at the green graph, now when I move b to the right, the green graph moves to the right. And when I move b to the left, the green graph moves to the left. And that's because I just included this minus sign in the actual formula itself. So whether you write it with a plus b, and then you have to remember that the slider works backwards, or whether you think about what number am I subtracting, either way, whatever is added or subtracted to x, the equation will move, or the graph will move in the opposite direction. Okay. Understanding why this occurs is a little bit tricky, but essentially, if you think about when we replaced x with x plus 2, what the graph was doing at 0, it now has that same behavior at x equals -2 because I added 2 to each of those x's and got 0, if that makes sense. So let me actually put my equation back in and do that again. So if I put y equals x plus 2 cubed minus x plus 2, that is this change with b equals 2. If I put in a -2 for x, each of these locations in the equation are going to come out to be 0. And that means that as x equals -2, the graph is crossing the x-axis and decreasing. That's the behavior that it has at x equals -2. So when I put in -2 for x, this spot comes out to equal 0, this spot comes out to equal 0, I have this behavior. If I put in 0 for x in the original equation, the cubed part equals 0, the regular part equals 0, and I have this same behavior. So the behavior that I get for x equals 0 in this equation, I get the same behavior in this equation when I make x equal to -2, because then these two parts of the equation come out to equal 0 in the same way that I got x equals 0 before. If that doesn't make that much sense to you, that's okay. You can just remember the rule that it moves horizontally in kind of the opposite direction. All right, let's look at the next one. So this next one is what I get if I multiply the entire equation by some constant number. So right now it's set to equal 1, which means multiplying by 1 doesn't do anything. But if I multiply by a number greater than 1, say multiplying by 2, that makes it taller. That's a horizontal or a vertical stretch. Notice that the x-intercepts are all the same though. I haven't moved the function over, and I haven't made the entire thing bigger exactly. It's not bigger in the horizontal direction, it's only bigger in the vertical direction. Or I could multiply the entire function by something less than 1, like 1/4, and now I made the whole thing flatter. It's not really wider per se, the zeros are still in the same place, but I made the whole thing flatter. I could also multiply by something negative. If I just multiply it by -1, that means that I get the same shape, but it is reflected over the x-axis. Because this function is odd, it actually looks the same whether it's reflected over the x or the y. But it's reflected over the x-axis when I multiply the entire thing by -1. Or I could multiply by something that is less than -1 and get both a reflection and a stretch. Or if I multiply by something between -1 and 0, I get a vertical shrink and a reflection over the y-axis. Hopefully that makes sense. Oh, 0, I just flatline. Okay, so that is a vertical stretch or a vertical shrink. And you can also have a reflection included in there based on whether c is positive or negative. If we multiply x by something, we also get a stretch or a shrink, but it's a stretch or a shrink in kind of the opposite direction that you would expect. So if we take x and we multiply it by 2, what this is doing in the equation is it's replacing each of these x's with 2x, and that causes the graph to get thinner. It's a horizontal shrink. Multiplying by 1, of course, doesn't change anything. Multiplying by something less than 1, or between 0 and 1, causes a horizontal stretch. Notice it's not a vertical stretch. The maximum points here are still in the same place. The minimum points are still in the same place. But the zeros of the function have spread out. It used to have x-intercepts at -1, 0, and 1. Now it has x-intercepts at -2, 0, and 2. So we've stretched it out in the x direction. We can also do a reflection. In this case, all the x coordinates are reversed. This one happens to look the same as when we did the reflection over the x-axis, but this one is a reflection over the y-axis. The reason that these two look the same is that it's an odd function. We can do a reflection and a horizontal shrink, or we could do a reflection and a horizontal stretch if we multiply by a fraction between -1 and 0. Okay, so just to clarify, something like this, how would I change the original equation? This would look like y equals -2 x cubed minus -2x. It's important to use parentheses here. If I didn't have these parentheses, it would not look the same. This is a different equation. There we go. So each time I replace every x in the equation with a -2x, that's what I'm doing when I do this y equals g of d times x, with d as -2. I'm saying to put into this function, instead of x, put in a -2x. Cool. We can also put these transformations together. So we're not always going to get a function that is just one transformation at a time. We could also get a function that combines them together. So right now, I have all of these kind of set to their doing nothing values, but I could take this original function and I could add to it. Oh, let me undo this one. So the red one is still the original. I could add something to the end. I could add or subtract something with x. I could do a vertical stretch or a shrink. I could do a horizontal stretch or a shrink. I could combine all of those effects together and get a graph that has sort of the combined effects of all those transformations. So, for example, compared to this red graph, this orange graph has a vertical shift up 2, a horizontal shift left 1, a vertical stretch times 2, and a horizontal stretch times 2. X is multiplied by 0.5, which means that it's actually getting twice as wide. Cool. We could change what function this is, and all of these effects would still be the exact same. But they look a little bit different with different functions. So recently, we've been looking at functions like y equals sine of x. And these have the same effects as the other ones. We can add or subtract a number to the end. We call that the midline when it's a trig function, but it's the same effect that we're already used to. We can add or subtract a number on the inside. Oops, I'm on the wrong slider. This has a name called the phase. This is one that we didn't really deal with trig functions because it makes the math a little bit harder, but you totally can horizontally shift a trig function, and we call that a phase shift. You can do a vertical stretch or a shrink. We call that the amplitude, but it's still the same effect that we have gotten before. We can do a horizontal stretch or shrink. That's related to the period. So this number that I've called d in this example would be the k, or the angular frequency, and that tells us something about the period. And this stuff is all really the same transformations as we had with the polynomial function, as we have with any kind of function. It's changes to the shape of it. And we can basically make any period, any midline, any amplitude trig function by doing these things. But let's at least set b equal to 0. For example, this sine wave has a midline of 3, an amplitude of 3/4, and a period of 4 pi. If we wanted to write this equation out, we could. It would be y equals, let's see, c is 3/4, so 3/4 sine of 1/2 x plus, what's a? A is 3. There we go. So this equation and this equation are really the same thing. I didn't write the b because b was equal to 0, and I wrote the decimals as fractions, but these two equations are really the same thing. And this one is one that should be more familiar, where you can see things like the amplitude and period. Another strong example of this is when we have a quadratic. And when we look at the combined effects of these transformations, we can basically move our function anywhere that we want and get any equation. So here's a totally different parabola from the one that we started with. let's see what this equation would look like. Y equals, let's see, C was 1, so I won't write that. And then I had D is 1.75. 1.75, I can write that as 7/4, but that's okay. 1.75 times x plus, let's see, b is -3, so I'll just write x minus 3. Our function here was squared, and then a is -3, so minus 3. So this and this are now the same equation because I wrote in the numbers for each of these places, and I replaced this g with the function we're actually looking at, which is x squared. And if you'll notice, this is basically what we call vertex form. So when you're looking at a quadratic equation in vertex form, what you're really looking at is the equation written in such a way that you can see the function transformations. And the reason it's called vertex form is that normally the vertex is here at 0, 0. Here now it is moved to 3, -3. And that corresponds to these 3's in the equation. So these same principles of function transformations are basically a connecting thread of all the different equations and all the different types of functions that we've studied. We could also look at them for exponential functions, but I think we'll wrap it up. So as you move forward in math, whether you're a senior and you're graduating and you're going to go to college, or whether you're going to take pre-calc, which I hope you do, this is kind of a central idea that will really help you see connections between every unit. And a lot of them, even though we have special names for them, like vertex form or like the midline and amplitude, are really the same principles over and over again, so that when you see them, they already kind of make sense to you and you don't have to relearn everything from scratch. All right, hope this was helpful, and I will talk to you again soon.